Last class, we were doing 3.1 examples, part 2. We did a non-rectangular section and an over-reinforced section. So both these examples are very important for your midterm, so make sure to study them. Okay, so we did a non-rectangular section, and you have a couple of other examples, as I mentioned. In tutorial 2, there's one example, and tutorial 3, which I will post during the weekend, you'll have a third example. Okay, so study these because these are probably going to come in the midterm, these non-rectangular sections. Okay, then we saw how to calculate the balance steel ratio. This, you have it on your assignment. So we saw 3 methods to get the balance steel ratio. And then we started an example where we had an over-reinforced beam. We mentioned when we have this over-reinforced beam, what's going to happen? This AS is larger than the AS balance, right? So in this example, we had AS, which was larger than AS balance, which we had found is 4,033 millimeters squared. But we mentioned we don't really need to do this comparison, okay? Instead, we just start by assuming that the steel is yielding as usual, and we solve for A. After we solve for A, then we get our C, and then we do our CD ratio, and we compare it to this limit. If we're above that limit, it means we're in the over-reinforced situation, okay? So then we said we have to be careful. Here, we don't have yielding anymore. So this calculation that we did for A is no longer valid. Same thing when we do the moment resistance check, it's no longer Fy here because we're not yielding, okay? So we went through that last class. We figured out it was over-reinforced. We found CD is 0.833, which was larger than our CD max of 0.636. Okay, so we said we need to revise our equations. And the way we did it is instead of having Fy over here, right? Instead of having Fy, we put Fs. So we put a steel stress. And then we define that steel stress because we are still in this elastic zone of our curve, right? We defined it using this equation here, using Hooke's law. Okay, so we replace this with this equation from Hooke's law. And then we were able to find a relationship for this strain just by using similar triangles, right? If I take these similar triangles here, knowing this one is here and knowing this is the strain epsilon S and knowing this is C and this is D, we can get a relationship for epsilon S. So we take that one, we put it into here, and then we take this stress equation and we put it into there. And then we said if we do a little bit of rearranging, we're going to end up with a quadratic. And this is what we found last class. This is our quadratic in terms of A. We can also have it, as I mentioned, in terms of C. And I think in the tutorial, I do it in terms of C. So both of them are fine, and you were able to solve the problem either way. Here, we did it in terms of A. We defined these different variables, and we ended up with this. So what's left? Now we need to solve for this A value. Okay, when I say in terms of A, you see here the variable which corresponds to X is A. If I use this equation 3A, then the variable will be in terms of C. Just here, you would put C times beta 1, right? If you wanted to use equation 3A, it's the same idea, but you would solve for C. Here we used equation 3B, so we will solve for A. Okay, so we just need to do this. So we remember our equation for solving a quadratic is just minus b plus or minus square root b squared minus 4ac divide by 2a. So if you do this, you're going to find two numbers. One is negative, makes no sense. So you reject that one. So you just keep this one. This one is accepted. All right, so that's what we did last class. So we don't have much left. We just need to finish now because now we know A. So we can determine this value of C here that we need to get this strain, and then we can get the stress, and then we're good to go. Okay, so let's continue now. So once we know A, we can solve for C and determine the strain epsilon S. Okay, so let's see here. So where's our C value? Yeah, so C C is just A over beta 1, right? Because I solved for A. If I had solved for C, right, if I had used this equation 3b, I would get, if I use equation 3a, I would get C right away. But we use this equation 3b, we solved for A, so now we need to convert it to this C value. So this is just equal to 377. Let me just make sure I have the right numbers here. This just, this one should be 377.3. Just correct this. Okay, double check that quadratic to be sure, but this should be 377.3. Okay, so we take 377.3 and then we divide by beta 1, which we had as 0.91. So that gives me 414.6 millimeter. Once I know this, I can use those similar triangles. So just so we understand where that similar triangle comes from, let's just draw this strain profile again to be sure. Okay, so here's our strain profile. This strain here is 0.0035. This thing that we just found, this 14.6, is the depth of the neutral axis. That's C. Okay, then we have this thing, which is here up to here. This is our strain epsilon S, and this thing is D. Okay, so we can get this equation. Epsilon S is just 0.0035 using similar triangles times D minus C over C. Okay, everybody sees where that's coming from. I'm trying to find this. So I know C and D now, and I know the one at the top is 0.0035. I can solve for this. So if I do this, what do I get? I will have 0.0035 D, which was in our question 600 minus 414.6 divided by C, which is 414.6. You do all this and you get 0.001565 millimeter per millimeter. Okay, or 1.565 times 10 to the minus 3 millimeter per millimeter. Okay, this makes sense, right? What was, if I look at my stress strain curve for steel, here's our yield stress, Fy equals 400 MPa. Okay, here's our modulus, is 200,000 MPa. And here at this point, we have our yield strain. What is our yield strain? It's just Fy over E. So that's 400 over 200,000. What does that give me? That gives me 2 times 10 to the minus 3. So does it make sense what we just calculated? It makes sense, right? We found something in here. The yield strain is 2 times 10 to the minus 3. So we're below that. That makes sense. We're not yielding, right? So therefore, not yielding as assumed, since epsilon S, which is 0.001565, is less than epsilon Y, which is 0.002 millimeter per millimeter. Everybody got it? Okay, so now I know this strain. Once I know this strain, I can find the stress. Okay, so again, we're in this zone here. So normally the steel stress is 400 MPa, but if we're in that zone, we're below yielding, we need to use this Hooke's law, right, to get it. Again, here you should look at the number you get, okay, to see if it makes sense. We have Fs equals to modulus times this strain epsilon S. So modulus is 200,000 MPa, okay, times epsilon S we found is 0.002 0.1565 millimeter per millimeter. Okay, if I do this, what do I find? I find 313 MPa. Does that make sense? Makes sense. So therefore, steel not yielding, and makes sense since Fs is smaller than Fy. If you do this calculation and you get 800, you made a mistake somewhere, right? The maximum stress you can have is 400. That's at yielding. Below, you're going to have this Hooke's law, and it should be always less than 400 MPa. We found 313. That makes a lot of sense. Okay, so hopefully that's clear, right? We found this thing. We're here. Fs equals 313. Okay, so once we have this, now we can find the moment resistance. How is it? It's the same thing as before. So same as before, but we use Fs, not Fy. Okay, so our MR is just going to be phi s as Fs times d minus a over 2. Okay, so this is what changed, right? We have this right here changed. So this is just 0.85. Our AS, if we remember from before, yeah, okay, so I should write this just to be consistent. Same thing, just rearranging here. Okay, so we have Fs, which is equal to 313. AS, if we remember, was 5,600 millimeters squared. D was 600, and then minus A over 2. So this A, we found 377.3 over 2 times 10 to the minus 3. So you make sure here, don't use the C thing, right? Use the A, right? Use this thing, A. That's what we need, because the stress block, rectangular stress block, is in terms of A, not C. C is the actual neutral axis depth. What's A? It's the depth of the equivalent stress block. Okay, so if we do this, we're going to end up with times 10 to the minus 6, right? Not minus 3. Times 10 to the minus 6, we'll have 612.9 kilonewton meter. Okay, so this is how you calculate the moment resistance of an over-reinforced section. Okay, I recommend see tutorial number 2, last example, for another example. Okay, if you study these two, the one we did in class and the one you did in the tutorial, you're going to be good for this type of problem. Okay, so are there any questions on this example here that I just did? All right, great. Okay, so let's continue. So that's 3.1 examples, part 2. We spent quite a bit of time, but we've done all these 3.1 examples. Let's now go back to beam design, lecture 3.2, and we're going to do a few examples related to beam design. All right, so this handout, beam analysis, we're done now. Beam design, we covered this handout, right? We've covered all this stuff here. We've looked at the minimum maximum reinforcement, the detailing requirements, serviceability, and so on. So all these things apply whether you do analysis or you do a design. Magda is asking, can you repeat what's A? Let me see if I have it in here in this handout. It's this, right? This is the depth of the neutral, not the neutral axis of this equivalent stress block, right? C is the depth of the actual neutral axis, the actual the limit between the compression zone and the tension zone, neutral axis. That's C. A is like what we use to get this equivalent rectangular stress block, right? So that's the difference between the two. Is that clear, Magd? All right. Okay, good. So let's continue back here. So this handout, as I mentioned, we already went through it. It covered most of the beam design. Okay, so let's wait for it. Loading. Seems to be stuck. Okay, so it covers most of the beam design requirements. They apply whether you're analyzing a beam or designing a beam. What's left? We need to know how to determine the amount of steel if we're given a factored moment. Until now, what have I done? I've given you a beam section, different shapes. I gave you rectangular, non-rectangular, and I told you to find moment resistance. What about if I'm doing design? Meaning I've done an analysis. I know what the moment I need to resist. I need to find the amount of steel I need to put in that beam. So that's the primary requirement in design. So let me just try to close this because it seems to be stuck. All right, 1 second. Beam design. Oops. Then we need examples. Okay, let's go back here. So let's go back to beam design. So as I mentioned, the primary design requirement is to find this moment resistance. So let's just read this: design versus verification. Up to this point, we have seen how to verify that a beam has sufficient moment resistance. Given a beam with defined cross-sectional and reinforcement properties, find MR. The design process is different. Here, you're going to have the factored moments that you determine based on loads. So based on loads, right, you would find this factored moment produced by the design loads. We'll have to design a beam by specifying the beam cross-sectional properties, the amount of reinforcement, and the distribution of the reinforcement. This process is iterative, so you can have different choices for the beam cross-section. Similarly, for the amount of steel, you might need a certain amount of steel, but you may choose to use 15 M bars or 20 M bars or 30 M bars, whatever, right? So there's different options here. So there won't be like a unique solution when you do design. Okay, so that's why I'm mentioning it's an iterative process and there's an element of choice. So these design requirements, they're in CSA A23.3 in these clauses 10.1 to 10.7. I mentioned this before. Don't just rely on my notes. You should download this standard. And every time when I cover a new topic, you're going to see I refer to these clauses. So it's good to go into the code and see what these clauses say. Okay, so the primary design requirement, the primary design requirements for RC flexural members in the ultimate limit states or strength is the strength requirement. The moment resistance must be greater than or equal to the factored bending moment. So MR needs to be larger than MF. This is the primary requirement that we need to satisfy. Normally, we will choose the beam dimensions first, then we'll choose a trial area of flexural steel to determine an initial estimate of amount of reinforcement AS. Okay. So this is one way to do it, but there's a way to solve for this AS using different methods. Okay, so we have to remember how we did our beam analysis. How did we do our beam analysis? We took sum of forces equal to 0. We set the tension force in the steel equal to the compression force in the concrete. So we did this before. Okay, and then we had this a rectangular stress block for the concrete with this depth A here. Here's our force of the concrete in compression. Here's our force in the steel in tension. And then we had this lever arm between the two, which was D minus A over 2. Okay, so if I'm giving you AS, what do? You solve for this A, right? We do as usual and we solve for A like this, and then we can continue as usual. But what happens now? We don't know AS. This one, we don't know it. So we can't get this A right away. Okay, so that's the first thing to remember. Then how did we get moment resistance? Let's say I knew how to get A. How did I do it? I took this force in the steel and then I multiplied by Z, which was D minus A over 2 if we had a rectangular section. So we ended up with this. But what's the problem now in design? I don't know this AS. And as I just mentioned, I don't know how to get A because it is also as a function of AS. Okay, so if I put A here, I took this A here, right, in terms of AS, and I put it into here. Right, I took this one and I put it into my formula here. Okay, then I'm going to end up with what's shown here. And then on this side, instead of solving for MR, I'm going to put MF, right? This is what we need. We need MR to be at least equals to MF. So to start, I can just set the target that we want is MF. Okay, so if I look at this, then there's different ways to solve this. One of them is to rearrange this equation, and we're going to end up with a quadratic. Okay, so that's what I'm going to show you on the next page. There's actually several ways to solve this. One of them is to do it directly. It's called the direct method. You just take these things. The only unknown here is going to be AS. And if you do a little bit of rearranging, it's going to end up being a quadratic. So this is called the direct method. Okay, there's another way, which is called iterative method, which I'm going to show you after the direct method. Okay, so in the direct method, it's a direct procedure. It determines the amount of tension steel AS by directly solving the quadratic obtained when setting MR equals to MF. So we have this here, we set MR equals to MF, so this is going to be a number. And then we have the only unknown is AS. We rearrange and we end up with this thing. It's going to be a quadratic, which is in this form. The only unknown here is this, right? This is the only unknown. So it's a quadratic in terms of AS, the area of steel, which is the area of required steel in millimeters squared. Okay, so all the other stuff, I'm going to have a number. What do I do here? I set MR equals to MF, right? So this is going to be a number. The only unknown is this area of steel. Okay, so we can solve for the area of steel. Again, it's a quadratic, so we can just solve it for this quadratic. These A, B, C, and the quadratic are just these values. We just be careful of the units here because we have lots of math. We just be careful to use the correct units as shown here. So I put MR in terms of Newton millimeter. I put B and D in terms of millimeter, F prime C in terms of MPa, and AS will get it in terms of millimeter squared. Okay, once we solve this, we're going to get a number. Let's say 3,357 millimeters squared. So this is the actual amount of steel I need. But then I remember in real design, what do I need to do? I need to choose a bar size. Either it's 20M, 15M, 25M, 30M. So that has a specific area. And then you have to choose the number of those bars. So I'm going to choose a number here based on the bar size. So 30 M's, there's 700 millimeters squared. So I look at this. I need 3,357. So then I can see I need at least 530 M to make sure I have a sufficient amount of steel. Hopefully you got that. And we're going to see it in the example. Once I do this, now I know the actual amount of steel is 3,500 millimeters squared. So I go into here. And now I do like we usually do in analysis. I'm going to solve for A, check for CD, and then get the actual moment resistance and make sure it's larger than MF. Okay, just here for the CD check, I mentioned in the current edition of the code, there's another thing called a ductility check, right? This one is making sure that the steel is yielding, right? And making sure that the assumption that we're using in the equations are correct. We always do that. But also now we also check this ductility requirement. We need to make sure this is less than this. All right, so let's look at an example because it will become much more clear. So let's go to 3.2 examples, beam design, and let's look at an example. Okay, so open this handout and we'll try to do this example. All right, example one, beam design example using the direct solution. Okay, so we're told for the reinforced concrete beam, which is shown, determine the most economical amount of tension reinforcement for the beam section such that the beam is capable of carrying a factored moment MF of 800 kilonewton meters. So this is based on the loads, right? So this is this one here, this is based on loads, we get this MF. Okay. Note, we're told to use 30 M bars. So here, just to make the solution more kind of keep us in the same region, we're going to say that we're going to use 30 M, but in real design, you'd have the choice, right? You can use 20 M, whatever you want. Let's here in this example, we're going to use 30 M. We're going to have 10 M bars for the stirrups, and we're going to assume we have a 30 millimeter cover. Okay. And we're told use the direct procedure. Okay. So here, there's some other properties. They've also chosen the cross section. So B is 450 millimeter and H is 900 millimeter. Also, F prime C here, they're telling us is 25 MPa. And then we're told use 30 M bars and 10 M stirrups. Okay, so that's what we're going to use. Okay, first thing we're going to do is we're going to calculate this alpha 1 and beta 1. Okay, so let's see here. So let me just be sure. So let's calculate the actual alpha 1 and beta 1 because I mentioned this a few times now, but you're going to see I'm going to use the approximate values. Okay, so alpha 1, the actual one is 0.85 minus 0.0015 times 25 MPa. It gives me 0.8125. Beta 1 is 0.97 minus 0.0025 times 25. It gives me 0.9075. Okay, so this is approximately 0.81. This is approximately 0.91. So if you want, you could continue with this, or we can use alpha 1 approximately 0.8 and beta 1 approximately 0.9. And this is okay if F prime C is between 25 and 40 MPa, which is what we have in this example. Okay, so if you want to use the 0.8, 0.9, as long as you're between 25 and 40, it's fine. But if I'm telling you use the actual exact values of alpha 1, beta 1, you should use these equation and get them. Okay. All right. Next, we're going to estimate D. Okay, so I didn't mention this here, but it's in this handout towards the end. So let me just go here. Okay, so if I know I'm using 30 M, 10 M stirrups, I know the cover, then I can calculate the actual effective depth. Okay, but sometimes you don't know what that bar size is. Okay, so this thing that I'm going to show you now, it's useful if you don't know the actual bar size. So I'm in lecture 3.2 here. I'm go towards the end here in the practical guidelines. Let's skip these here. And let's look here. So this is a way you can estimate the effective depth D as a good starting point if you don't know what the bar size is and so on. So if you have one layer of reinforcement, you can estimate this D. It's going to be approximately H minus 70 millimeters. So you're going to see now when I'm going to do this example, I'm going to use this. Okay, so that's where that comes from. It's on page 15 of this lecture 3.2. Right, so let's estimate D. So if you know, again, the bar size, you know you're going to place it in one layer, you know the cover, you know the stirrup, you can calculate the actual effective depth. But here, let's say we don't know that stuff. So we're going to do an estimate of D. So let's use an estimate. An estimate, okay, for one layer of steel. This D is approximately H minus 70 millimeters. So this is 900 minus 70. It's 830 millimeter. Okay. So that's our estimate of D. Next, we're going to recall our equation. We're going to set MR equals to MF. So set MR equals to MF. And then here, we're going to solve for AS required. Okay, we're going to solve for AS required. Okay, so we're going to rearrange. We're going to end up with this quadratic here. So this first part, this one here, this one here, that's this. Yeah, that's our A in here. So if we do this one, we're going to have it's equal to 0.85 times 400 squared divided by 2 alpha 1. This is where I said you can use the actual alpha 1 of 0.81, but I'm going to stick with the 0.8. Okay, so I'm just using 0.8 here. Times phi c 0.65 times f prime c of 25 times b, which is 450. So if I do this, I'm going to end up with 9.88. Okay. So again, you can put 0.81 here. That's also valid and it's fine. Okay. But I said I can use 0.8 because we're within that 25 and 40. That's also good because it's approximately good. Okay. So B is what we have here. So B is this thing. Okay, so I'm going to make sure not to forget the minus. So I have minus phi s times Fy. So minus 0.85 times Fy, which is 400, times D, which is 830. This gives me minus 282,200. Okay, and here we're going to set this one. Set MR equals to MF, which was 800 kilonewton meter. So here I'm going to set this equal to MF. So it's 800 kilonewton meter, but I said be careful of the units. So I'm going to put everything here in newtons and millimeter, right? So I'm going to be careful. I take 800 times 10 to the 6 Newton millimeter. Okay, once I have this, I can solve for this quadratic. And if I do that, solving, so try it on your own later, just to make sure I didn't make any mistake. Solving the quadratic, you will get x equals to 3,191 millimeters squared. Okay, now what do we need to do? So that's the amount of steel I need. I need 3,191 millimeters squared. What's next? I'm going to select the bar size. So here we're going to use 30M bars. Okay, but as I said in design, you usually have a choice of what you use. So I'm going to use 30M. And then you're going to select the number of bars. Okay, so here I have to be careful. I need at least 3,191 millimeters squared. So each 30M, if we look back in that table that gives us these areas, is 700 millimeters squared. So how many bars do I need? So I need AS larger than 3,191 millimeters squared. So what am I going to use here? How many bars should I use? Is 430Ms okay? What do I need here? I need 530Ms exactly. So use 530M. That gives me 3,500 millimeters squared, which is bigger than AS required, which was 3,191 millimeters squared. Everybody sees here, if I had used 20 M's, right, I'd have a different bar size and I would choose a different number of bars. Okay, so we have this. So we're going to use 3,500 millimeters squared. Okay, so now we do this verification. So this is what I was just saying here. Let's select 30M bars. Each 30M bar is 700 millimeters squared. How many 30Ms? We're going to use 5 30Ms. And then the actual area of steel is 5 times 700 is 3,500 millimeters squared. Okay. Hopefully everybody was done what I did here. Both values are positive. I think one of them should be negative, Emil. I'm not sure, but I think you get a negative. What do you get as the two values? Okay, so I think one of them will be positive, another negative. So you guys can try that. If not, you can post it on the, okay. Not sure, double check your math. If not, you can post your question on the forum. Emil, that's a good question. So I'll look into that. But I think one should be negative, one positive, if I'm not mistaken. All right, let's continue. So Emil, you can post that on the forum, or if you forget, I'll try to remember this and get back to you. Okay, so next, let's determine the actual effective depth. So this is D, right? Now we know we're using this here. Our depth here, H was 900. We're using these 10M stirrups. And here we're putting 5 of these 30Ms. Okay, the cover, if it was not given, it was given in the question, I believe here. If not, you'd have to select it based on the exposure condition. So cover is 30 millimeter. Normally, if the beam is inside the building, it's 30 millimeter. Okay, so now we can determine, and we're using one layer. So now we can use the actual effective depth. So we have 900 minus the cover, which is 30. So this is the cover, minus the stirrups. So this is the 10M stirrups, minus half the bar, 30 over 2. So this is dB over 2. Okay, so if I do this, I'm going to get 845 millimeter. You can see the 830 that we used as an estimate, it was not bad. There's 6 steel bars. Okay, maybe I made a mistake drawing. So there we go. All right, for heating is 530Ms. Okay, so 845 is the actual effective depth. We had assumed 830 in the initial estimate, but the actual one is 845. So now we do the verifying of the design. So let's calculate A. A we're going to get from here. So this is 0.85 times area of steel is 3,500 times Fy, which is 400, divided by alpha 1, which is 0.8, times phi c, which is 0.65. F prime c is how much here? What are we using? We're using 25 MPa. And then the B, which is this thing, in our example, it was 450. Okay, times 450. Okay, so everybody sees here what I'm putting in. Use AS actual, okay, what we used for design based on the 530M. Okay, so if I do this, I'm going to end up with 203 millimeter. Okay, now I do this MR check. So MR now is equal to phi S, so 0.85 times AS. Again, I use the 3,500 times 400 for the Fy. D, I use the actual D, 845 minus A, 203 over 2 times 10 to the minus 6. And if I do this, I'm going to end up with 884 kilonewton meter. And now I do my check, right? I need to check. Is this larger than MF, which was 800 kilonewton meter? So I have to do this check here. If I did everything correctly, it should be, right? So I find 884, it's bigger than MF equals to 800 kilonewton meter. So this is okay for the design. So we did everything okay for the design. Okay, but we need to do this check, right? Always, whether we're doing analysis or design, we need to do this check. We need to do the check to make sure that the steel is actually yielding, okay? Because if we put too much steel, it's not yielding and it's not good. So we do the CD check. So C is equal to A over beta 1. So this is 203 over 0.9, and I will find 225 millimeter. That means C over D is 225 over 845, which is 0.266, and we need to make sure it's smaller or equal to CD max, which was 700 over 700 plus FY, which we said is always 0.636. Okay, so we can see here it is okay. So it's okay. The steel yields. Okay, then we should also check the other things. So there's also ductility check. In CSA 823.3-19, we need to make sure that CD is smaller or equal to 0.8 of this, which we said is 0.51. We can see here this is 0.266. It's smaller or equal to 0.51, so this is also okay. So that means it is also ductile according to the code. Everybody got it? Okay, what are the other things to check? You need to check AS min. So we're running out of space here, but I need to check AS min. So I'll use this one. So this CD check that we did is like the maximum area of steel. Now we also check this AS min. This AS min, we're going to use this option too. So AS larger than AS min. We were checking this. So AS min is equal to how much here? It's 0.2 square root of F prime C, square root of 25, divided by Fy, which is 400, times BT, which is this width here in the tension face, so times 450, times H, which is 900. If I do this one, I'm going to end up with 1012.5 millimeters squared. So since AS equals 3,500 millimeters squared, it's larger than AS min. So this is also okay, right? So this is okay. What are some other checks that we need to do? Shane is asking, can I do MR larger than 1.33 MF? Yes, but here you're going to see it's not, right? Because we're trying to be efficient, right? We find 884, it's larger than 800, but it's not 1.33 times larger. Okay, so if I had put like a lot more steel, then you can skip this AS min check. But usually we don't do that, Shane. Okay, so we do this AS min all the time because we try to be as efficient as possible.
Okay, thanks.
Okay, Abdullah is asking, why is there 7 bars in the diagrams? There are 5 bars, there should be. These ones here, you're talking about these, Abdullah? Okay, these are compression bars or just there to hold the stirrups. Good question. Okay, Abdullah. So these ones at the top, they're usually just small bars. They're not there to give me any like moment resistance. So we usually ignore them. But you're going to see later, sometimes we put bars right there on the top for a specific reason. Okay, and then we need to account for them in design. It's called a double reinforced section, which we're going to see maybe next week. Okay, so good questions. All right. So what are the other checks that we would need to do? Okay, so we're usually not done here, okay, because we put 530M, but we place them in one layer. What are some other checks? Who can tell me if you can remember what we did before? What's one that I would definitely need to check? I'm placing 530M in one layer. What's another check I would have to do to make sure it's good? Good, bar spacing. So you would check that. I'm not going to do it here, but let's say it passes. Okay, what's another one that we would need to do that we saw before? This is due to serviceability. We saw there's a couple of things we should check for serviceability. There's a factor. It's called a Z factor. Check. You need to check the Z factor. Number of layers is with the bar spacing, right? If the bar spacing doesn't pass, then I would need to place it in 2 layers, and that would actually we'd have to redo a lot of our analysis again. Okay, but that is covered in the bar spacing. Usually we try to place in 1 layer. Okay, if it doesn't pass in the 1 layer in terms of bar spacing, you place it into 2 layers. Okay, so Z factor, we have skin, reinforcement, and then we check that the cover is okay. And then we have deflection. Okay, make sure H is larger or equal to this H min. Okay, so the same stuff we saw for analysis, they would apply here. Okay, so in terms of like an assignment or midterm, I'll tell you what you need to check, right? So I'll tell you the specific things you would need to check, but that's how you do design. Hopefully that was a clear example. On page 10, is that the main bar spacing equation? I'm not sure which page 10 you're talking about, Magd. Page 10 here. Let's see here. Yeah, they're all in this, right? So all these things I mentioned, they're in here. The stuff I was saying. Bar spacing requirements. Page 10, I said, yes, usually that's it, right? But I said don't like memorize that equation, try to figure it out where it comes from. But usually this is it. It's the bar spacing in the 1 layer. Okay, yeah, usually you have the width, and then you have the 2 side covers, you have the D of the stirrup, and then the number of bars. So yes, this will almost always be the equation you need to use to check bar spacing. And then you check them against these things like we saw. All right, so that's one way to do this analysis. Let's see another way, this design. Let's see another way. So this is what we just did, which is the direct method. Everybody's done here, so I can go back to the notes. All right, so we just covered the direct method. We directly solve the quadratic. Okay, it's good, but it takes a bit of time. There's another way, which is called iterative method. The iterative procedure determines the area of tension reinforcement by estimating the depth of the compression stress block and then recalculating until accuracy has been achieved. Right here, why did we end up with a quadratic? Because we said A is in terms of AS, and then also we have AS here on the outside. So if we can estimate what A would be, then it would save us some time, right? So this is what we're going to do in this iterative method. So we take our same equation, we set MR equals to MF again. The unknowns are AS and A, but we're going to do a preliminary estimate for A. Okay, so in beams, usually this A is going to be approximately 0.3D. Okay, so I can use this and use it in my analysis. We'll see later something called one-way slabs. We'll use a different estimate for that. But for beams, a good starting point for A is 0.3D. So if I put in here, right, I put A equals 0.3D. This equation would end up being like this, and the only unknown here would be AS. So it's going to be much faster. Okay, so here, what did I do? I did D minus A over 2, and then I set A equals 0.3D. This is just going to be D minus 0.3D over 2. So it gives me 0.85D. Everybody saw where I get this here? So it's an estimate for A that I'm putting in there that gives me this equation. Once I know this, I can just rearrange this and solve for AS. Okay, once you solve for AS, it's not going to be the actual one I need. Okay, so I need to calculate this AI that I'm going to say. I'm going to put in the AS that I just found and calculate A. If A is within 5% of the initial estimate of 0.3D, I can just stop there and continue. But usually it's not going to be. So if it's not, then I'm going to solve for AS again by taking this one here and putting it into here and solving for AS. And then I go through the whole thing again. I calculate A. I see is it within 5%, 5-10%. If it is, I stop. If not, I just keep going like this in an iterative way. Usually 2 iterations, 3 iterations is going to be enough. And I'm going to end up with the AS that I need. Once I know the AS I need, the rest of the procedure is exactly the same. So once I know I need these 3,000, let's say 357 millimeters squared of bars, then again, I choose the bar size 30 M, and then I choose 5 30 Ms, and then I just do the same exact verifications we saw in the previous example. So this is just another way to solve for this AS that we need. Okay, so again, it will make more sense by going through an example. So let's go to 3.2 examples and keep going. Let's go here. Okay, so this is the same example we just did, but we're going to do it with the iterative procedure. So let's do this again. So alpha 1, beta 1. So I'm on 3.2 examples on page 3. We're doing iterative method. Okay, so alpha 1, beta 1 from before. Alpha 1 equals 0.8 and beta 1 equals 0.9. Estimate D from before, same way as before. D is approximately H minus 70. So we have 900 minus 70, that's 830 millimeter. Okay, just like before. Let's estimate A. So to estimate A for beams, A is approximately 0.3 D. So 0.3 times D, it's equal to 250 millimeter. Okay, so this is our initial estimate for A. So then I can use this here and plug this into here. So I'm going to end up with this equal to phi S AS FY 0.85 D. Okay, so let's do this. So I'm going to solve for AS. So AS, and here we're going to set this equal to MF. So set MR equals to MF equals to 800 kilonewton meter. So this is just going to be equal to 800. Again, I'd be careful of the unit, times 10 to the 6 Newton millimeter divided by phi S, which is 0.85. So this is what I'm trying to solve for here, right? This, I'm trying to solve for this. So I put that here, times 0.885 times Fy, which is 400, and then times 0.85 D, 0.85 times D, which is 830. Have I made any mistake here? I don't think I have. So this gives me how much? It gives me 3,340 millimeters squared. Okay. Technically, you can just stop here. Okay, just stop here, choose 530 M and check, and it would work, right? But if you want to get a better estimate, you do these iterations. Okay, so I want you to do these iterations. So we're going to start with this. This is it's a good start, but it's not like a really close estimate. So let's go through this. So check the estimate. We're going to calculate this A1. Okay, so A1 is just phi S, so 0.85 times AS, so this 3,340 times 400 divided by alpha 1, which is 0.8 times phi C, 0.65, F prime C, 25, and then B, in this example, it is 450. Okay, so if I do this, what do I end up with? I end up with, if I haven't made any calculation mistakes here, it ends up with 194 millimeter. Okay, so what do I do now? I take this one that we had in the beginning. This. right? I look at this one and I compare to the one we just calculated, right? We just calculated it and it's 194 millimeters. So I then compare, is it within 5% of our initial estimate? So I can see A1 is not within 5% of A initial, right? A initial is this one in yet this one here, this one. So that 250 millimeter, and the one we just calculated is this one. Oops. Okay, it's this one. So we can see 194 is not close to the 250. It's not within 5%. So I should do an iteration. So I do iteration 1. So for iteration 1, we're going to take this here and we're going to plug in AS equals 3,340 millimeters squared. So I'm going to take this one that we calculated above, this one. I'm going to take that here. Okay, and then I'm going to solve for no, sorry, I made a mistake here. Okay, so I don't plug in the AS. That doesn't make sense. I'm going to plug in A, okay, A1, which is 194 millimeter. Okay, sorry about that. So we're going to plug in this A1 of 194 millimeter into here. Okay, so then I'm going to solve for AS again. So if I do this here, I will have just a second here. So I'm going to have AS equals to 800 times 10 to the 6 Newton millimeter divided by 0.85 times 400 times D minus A over 2. So I be careful. I put D minus A over 2. So I put 830 minus A over 2. I put this 194 over 2. Everybody followed? So I took this A1 that I calculated here and I plug into this equation and then I solve for AS. So if I do this, I'm going to find 187 millimeter. No, 1 second. It's not right. So if I do this and I solve, I'm going to find 3,233 millimeters squared. Okay, so I solve and I get 3,233 millimeters squared. So then I'm going to put it into here. So I take this one and I put it into here and I'm going to get my estimate for A2. So A2 now is equal to phi s, so 0.85 times this thing that we just found, 3,233 times Fy, which is 400. Okay, divide by alpha 1, 0.8, phi c, which is 0.65, F prime c, which is 25, and then we have 450 millimeter for the B. So if I do this, I'm going to end up with, what do I find here? I'm going to find 187 millimeter. Okay, so this is our new estimate of A. So then we compare A2 and A1, and we can see it's within 5%. So A2 is the one we just calculated here, the 187. We compare it to A1, which is this one. So this, just to be clear, this is 187 and this A1 is 194. Okay, it's pretty close. So then we can stop. Therefore, stop. Okay, everybody got it? If it was not close, I just do one more iteration. Usually it will be good after the second iteration. This 5% is not like a fixed value, right? It's an approximate thing. Like if you're 6%, 7%, usually it's okay. Okay, but if you're more than that, like 10%, you should probably do one more iteration. Okay, So that's close enough. So once we have this, we need AS larger or equal to 3,233 millimeters squared. Let's use 30M. So if we do 530M, that gives us 3,500 millimeters squared. Okay, so what would we do next? After that, proceed like in previous example, right? What we do here, we just continue as before. I'm not going to do this calculation again. We would calculate the actual, right? It would be what we just did before. It would be 845 millimeter. Then you would calculate A actual, like in the previous example, and we would find, so we would just do phi S, AS, FY, alpha 1, phi C, F prime C, B, right? And here we would put in this 3,500 millimeters squared, right? Like in the previous example, and we would find 203 millimeter. And then we would calculate MR using this phi S, AS, FY, D minus A over 2. Again, we make sure here we use this 3,500. Okay, if you do this, you will find 884 kilonewton meter, which is larger or equal to MF of 800 kilonewton meter. So that's okay. Then you would check CD smaller or equal to CD max. You would check ductility. And then what else? You would also check AS min. So basically exactly like we did in the previous example, right? This is C, previous example, exact same steps. So the only thing that was different is how we found this 3,233 millimeters squared. After we do this and we choose the 530 M's, it's exactly like we saw in the previous example. Are there any questions on this one that we just saw? So this is called the iterative method. Okay. So just to be clear here, in here, you would use this 3,500, same thing here. And then here, you would also make sure use D equals 845 millimeter. Okay, other than that, it's the exact same thing. All right, hopefully that's clear. So that's another way to do this analysis. Okay, we have 8 minutes. Let me just see the third way. And if we have time, we'll do it. If not, we do it next time. Okay, so that's the second way of doing the analysis. What's the third way? It's using those concrete design handbook tables. Okay, we saw it. We can use it for beam analysis. We can also use it for beam design. Okay, so if the beam is rectangular and it has tension only reinforcement, we can use that table. We saw table 2.1 to solve. Okay, the only thing is now we're going to do it backwards. Okay, instead of solving for KR, instead of solving for MR, we're going to solve for a KR that's needed. Okay, so we're going to set MR equals to MF. And then in that table, we're going to look for the KR minimum that we need. Okay, we set this MR equals to MF. We just divide by BD squared. That's going to give us, because remember, MR, if we use table 2.1, how do we get the MR? It's just KR times BD squared, right? So here we set MR equals to MF. So this is a number. And this is also known, right? We're going to know B and D. So then we solve for KR minimum or KR required. Okay, so we're going to find the KR that we need. And once KR is selected, we find the row value that corresponds to that KR. And then we can proceed with our design. Okay, so let's, again, it's more clear if we do an example. We have 6 minutes. Let's see if we can beat the record and do it in 6 minutes. All right, so here's the steps again. We're going to set MR equals to MF. We're going to solve for a KR min, which is MR divided by BD squared. So all these are numbers. We're going to get a KR min. Then we go into table 2.1 and we select a KR which is larger than this KR min that's needed. Okay, then we find the row that corresponds to that. And then once we know row, we can multiply by BD and find the area of steel we need. And then we always do a verification. So then we find the KR that we're actually using times BD squared and so on. So let's see example on this. All right, so let's skip this here. Let's go here. Beam design, page 4 of 5. We have the same exact cross section. So let's look at this. So we set, okay, just to make this less iterative, in this example, let's assume we have 30 M bars. They're placed in one layer. We have 30 millimeter cover. Okay, and then we also have 10 M stirrups. So we already know we're going to place 30 M in one layer just to make things easier. So we're going to calculate the actual. So calculate the actual. Okay, if you didn't know, you can also go through the use D estimate. Okay, so let's just be clear here. Okay, so D estimate we saw like before is just H minus 70. So that would be 830. But here in this example, just to save a bit of time, let's use the D actual is just H minus the cover minus the 10 M stirrup minus DB over 2. So this is just 900 minus 30 minus 10 minus 30 over 2. And I'll find 845 millimeter. Okay, so let's use the actual, but you can also do it with the estimate. You're just going to make sure to verify your analysis at the end. Okay, so let's use the actual. We set MR equals to MF, which is 800 kilonewton meter. Okay, so then we solve this KR required. We have 800, be careful of the unit, times 10 to the 6 Newton millimeter, divide by BD squared. So divide by 450 times D 845 squared. So this is what I'm saying right here. You can put in 830. It's also fine. You'll just at the last step, make sure to use the 845. But just to save time, I'm just using this 845 here. And we'll end up with 2.49. Okay. Then you go to table 2.1 and you choose KR larger than KR required. Okay, so the inputs are F prime C. What are the inputs? It's F prime C, which in this example is 25 MPa, and KR required, which is 2.49. So I'm going to show you in the table, but let's just write it here just to start. So at KR equals to 2.5, we're going to find that the rho is 0.82%. And then the next entry at KR equals 2.6, we're going to find rho equals 0.86%. So what we're going to use here in this example is this one. And we can even put at KR equals 2.4. Let's check that in the table. Okay, so we're going to get these entries here. Let me open that. Okay, so here's our table 2.1. Now it's going to be hopefully more clear. If I look at table 2.1, I look in here. So we're at 25 MPa. We said KR required was how much? We said, how much do I need? We calculated we needed 2.49. So I need to choose something at least 2.49. So I look in here and I keep going down here and I focus on this 25 MPa column. So I need at least 2.49. So I'm looking in this column here. Go to 2.49. I can see for 2.4, it's 0.79 for rho. At 2.5, it's 0.82. And at 2.6, it's 0.86. So that's how I got these numbers, right? These are rho values and these are KR values. So I have these things. That's where I got them. Okay, so this one, 0.79%. Here, we need KR bigger or equal to 2.49. So this is close enough, right? If it was not close enough, you do an interpolation to find the rho that you need. But here I can see 2.49 and 2.5, almost the same thing. So I'm just going to continue with the 0.82%. Okay, so let's use KR equals 2.5, and that gives me a rho of 0.82%. We'll get a rho of 0.82%. So the AS that's needed is rho times B times D, so 0.82 over 100 times B, which is 450, times D, which is 845. If I do this, I'm going to end up with how much? I'm going to end up with 3,118 millimeters squared. Okay, so I found this 3,118 millimeters squared. Okay, we ran out of time now, so I'm going to stop here. But we have this AS that we need. Okay, what are we going to do next? We're going to choose the type of bar. So here we're going to use 30M. And so we are going to choose an AS which is larger than 3,118 millimeters squared. Here we're going to means that we need 530M. That gives me 3,500 millimeters squared. What's left? We need to calculate the actual KR that corresponds to this, right? Like we did in the previous two examples. Once we choose the amount of steel that we're actually using, then we go through the calculation again to make sure our MR is okay. So we're going to use this to find the KR actual, right? That's the next step. And then once we know it, we're going to verify that MR is larger than MF, and then we'll do the other checks. So that's this example. We did 90% of it, but we have a little bit left. So we'll do that next week when we come back. Are there any questions for today before we end the lecture? Okay, so the main things to retain from today, we said the midterm is going to stay on February 17th, so in 2 weeks' time. The second thing we said is the assignment and the quiz. So assignment 2 and lab quiz 2, you have until Sunday to complete that. Okay, that's all for today. Okay, everybody. So have a good weekend. We'll see you guys next week. Mag, do you want page 2? Here.